Okay, so in this video we're going to talk about right and left limits. And we'll start with an example here. So let's say we have a function. It's increasing and it jumps up at, let's say this value, this x value is 5. And say it jumps from 2 to 3 here. Okay, so if we try to compute the limit with this function, and we pick values that are less than 5, we'll get outputs that are close to 2. If, however, we pick numbers that are greater than 5, the outputs are going to be closer to 3. So as we get closer and closer to 5 from above 5, we're getting outputs that are close to 3. So the limit as x goes to 5 of f of x does not exist, because the outputs are approaching 2 or 3, depending on if we approach 5 from above or below. Now we still see that we can say something about this function, because it's clear that if the numbers are above 5, the inputs are above 5, then the outputs are going to be going to 3. So this is where right and left limits come in. So what we do is we say if we're approaching 5 from above, or from the right, with this little superscript plus, so values that are bigger than 5, then those are going to be, those outputs are going to be approaching 3. And if we approach 5 from below, from the left, 5 minus, superscript minus, then we're going to have outputs that approach 2. And this is the idea behind right and left limits. So let me just write down the definition for your notes. So the definition goes like this: limit as x goes to c plus of f of x equals L means that the f of x, the values of f of x, approach L as the input values x approach c from above, or x is greater than c. This is the a right limit. This is the definition of right limit. So in a similar fashion, the left limit is going to use the superscript minus superscript, and the values are going to be less, the x values are going to be less than c. The inputs are going to be less than c. So this is the left limit, limit from below, and this first definition is the right limit. Okay, so now that we have the definitions out, let's do another example. I'll call this example 2. So let's just draw a quick picture here. 1, 2, 3, 4. Let's say we have a function that comes up diagonally, has a hole at 2, and then on the other side it has an asymptote. So like goes up like that, and then it jumps at 3 and comes down to 4. Something like that. Okay, so let's compute some limits. Let's do the limit as x approaches 2 from below, from the left. Limit as x approaches 2 from above, the right. Limit as x approaches 3 from below. And limit as x approaches 3 from above. Okay, so let's do the left limit with 2 here. So we're going to pick a value that's really close to 2 and below 2. And you can see that the numbers that those outputs are approaching are 2. As we get closer to 2 from below 2, the outputs are getting closer to 2. All right, in a similar fashion, if we approach 2 from above, we can see that these output values are unbounded. They're kind of going to infinity. So they're not existing, or you can say infinite. Infinity is just a more descriptive way of saying does not exist. Okay, now let's look at 3. So if we approach 3 from below, get an input close to 3, you can see that the output is getting close to 2. And if we approach 3 from above, then the output is 3. Okay, so even though there's that jump there, we have right and left limits existing at 3. Just a note, if the right and left limits agree, then the limit exists. And it's that common value that they both go to. Okay, let's do another example. So let's compute the limit as x goes to 2 from the right and the left. When f of x is this rational function x squared minus 6 over x minus 2. And this is a good one to do algebraically, because if we put 2 into this function, we'll see that it's undefined at 2. So we have to pick numbers that are close to 2 to estimate or figure out what this limit is. So we could graph this. I'm going to do this in a slightly different way than I've done the other examples. I'm going to do this with a table. So the way I'm going to do the right limit is I'm going to pick values that are above 2, and then I'm going to pick values for the left limit. I'm going to pick values that are below 2. So we'll start with 2.1. That's a value that's above 2 and not very far above 2. And then we'll put numbers that are even closer to 2, but still above 2. And we'll see what the trend is. So if you put x squared, or 2.1 into x squared plus x minus 6 over x minus 2, you'll get out 5.1. If you put 2.01 in, you'll get 5.01. And if you put 2.001, you'll get 5.001. So you can see that as we're approaching 2 from above, the outputs are approaching 5. So it appears, algebraically at least, that this right limit is 5. This is just a guess, an estimate, but the graph would confirm that this is true, and we could do this using the limit laws from earlier. Okay, now let's do the left limit. So now we got to pick values that are below 2, like 1.9, 1.99, 1.999, and these are all approaching 2. Let's see what the outputs approach. So if you do this with your calculator, you put 1.9 into this, you'll get 4.9 as an output. If you put 1.99, you get 4.99, and then you'll get 4.999 when the input is 1.999. So again, we're seeing that as we approach 2 from below, we're getting 5. And since the right and left limits appear to be the same, it appears that the limit does exist. Now later on we'll see how to do this more rigorously, but for now this tabular way of doing it is a good way of estimating or guessing what the limit is. Alright, I hope you found this video useful.